The difference engine, Babbage's analytical engine, the best engineering analyses that have been published is it probably couldn't turn. It's just too many gears, too many trains, too many cams and levers and widgets. It's just not physically possible to operate. So
it's a steampunk computer.
It's a steampunk computer. So we wanted a computer that we could actually build in the 17th century.
And use.
Okay, and use. We wanted to be able to build four-function calculators because abacuses are cool, but they're hard to learn and they're a pain. And I'm lazy.
How many of you know what the Coanda effect is? Oh, there's a few of you.
Cool.
Well, I've been
Cool.
here.
We've seen it before.
Yeah, right. The Coanda effect is this really neat idea that when you have a stream of anything, it attaches itself to a surface. Y'all have stuck your finger under a running faucet and noticed how the stream of water hung onto your finger and displaced off to the side, right? Everybody's seen that. So that's the Coanda effect. The stream will cling to a surface, okay? So if you have an input, a power stream like this, and you have a disturbance in that power stream, you can move the cling from one wall to the other with a little input. So you can move it from here to here. Now, what happens?
Do that.
What happens if you have a divider there? Now I can direct this one way, and I can direct that another way from a control source, can't I?
Binary.
I have a toggle switch that's operated by a control source. I've got a binary switch, right?
Effectively a fluidic transistor.
Effectively a fluidic transistor. So here at the bottom we have the divider, right? With the power stream and no input, the output goes that way. With the power stream and an unbalanced input, it gets diverted this way, and it changes and it clings here. The Coanda effect says it stays. I don't have to leave that on.
You just have to push it once and
I have to push it once and it stays. So I have a flip-flop in one part.
with no moving.
With no, well, yeah, I've got moving. I've
just
got
the moving
air
fluid.
or the water stream.
Right.
Right? But I've got no valve.
There's no mechanical.
There's no mechanical component. I have no valve. So I have a flip-flop that operates from steam, air, water, whatever you want to pump through it. Okay?
All we need is a computer key.
Now all we need is a computer key because 3 flip-flops makes an adder.
Now you would think that this would be a little abstruse for a small town in West Virginia, but about 10% of all of the water meters out in front of your house
Work that
in
way.
North America are Coanda effect water meters.
Yeah.
Because at the bluff body, the thing in the center, at the bluff body there is a pressure change when it flops. And a very, very, very simple pressure indicator can be used to count that.
Tick, tick,
And
tick, tick.
it just so happens that the frequency of the flops is directly proportional to the flow of the fluid.
Right.
So it's a real easy water meter, and a lot of people use it.
Part of the reason, when I wrote 1632, part of the reason I chose a town like Mannington, it's a very working class, blue collar kind of town with relatively small number of college graduates in it. But this kind of knowledge is a very, very
Basic.
basic and widespread
And
in that kind of town. Whereas if I take it Evanston, Illinois, about half population would be college professors, they would have been able to explain this theory a lot better. I don't think they would have survived more than about 6 months.
I don't think so. So
That's generous.
That's generous.
Speaking as a college professor.
Yeah, I know.
It's
so
all right.
You
You
see
redo
how I
yourself.
can make a computer with no valves, nothing
not
that's
a-
going to move
I'm not
except
of my
the fluid,
town.
right? Okay. If you Google fluidic computers sometime, you'll discover that people have built hobbyist systems with up to 30, 40 gates, and they work just fine. Okay. In the 60s, Bendix came up with the incredible idea that they could use this to control machine tools because it was hydraulic and it was all neat. But the problem was, of course, by that time in our world, electronics was already well developed, right? And so to compete with electronics, they had to make their systems very, very small. Okay?
Miniatures.
With channels that were on the order of less than a 64th of an inch. Okay? What's it take to plug a channel that size?
Everything.
Yeah, right. Literally nothing. Turns out that the ability of the oil to accidentally take some humidity out of the air was enough to froth it enough to stop them from working. And so every fluidic Bendix controlled lathe in the world got it ripped out and replaced with a piece of electronics. But they do work. So in 1632, we upsized the channel, right, to make it a reliable thing. And we also take advantage of the fact that they're making bleach, and we run bleach water through it.
And we put a filter.
And we put a filter in place.
Most
but-
of all, they're not competing with jillions of integrated
Right.
circuits being, produced in Taiwan.
Exactly.
The other thing is the ones on the bistable or two-state device pictures there. Those can actually be cast ceramic.
Which is where I was just, yeah, thanks, Walt. That's exactly right. So imagine this.
Well, I thought it up, so I
It is. It's extremely cool. So imagine this. Lay out your circuit with, notice that these are two-dimensional, right? Just like integrated circuits are two-dimensional. They exist in a plane.
I'm not going to say the L word. You can do that.
No. These are two-dimensional. So, roll out a piece of clay. Make a mold that's the size and shape of your flip-flop. Punch it into the clay, make the channel to the next place, punch it into the clay, make the channel to the next place. Or better, lay out your entire circuit all at once. Put it on a press and go, yeet, with a release agent. I admit this is fussy work, but trust me, artisans are capable of fussy work. But you do that, you fire it carefully so that you get the right shrinkage, you let it dry carefully, and you'll have a lot of rejects, just like Intel does, Intel has a lot of plates that they image that they throw away. And so, but the point is, we can take an entire circuit
All at once.
all at once, stamp it into a piece of clay, dry it, fire it,
Bake it.
right? Bake it, and then we can take the next piece of circuitry with a vertical connection, right? Cover that bottom layer with a bit of wax, stack the next layer on top of it so the vertical connections line up, and the next one for however complex a circuit you need, and then we put a plate across the top. Okay? So, with that, using channels between 1/8 and 1/4 of an inch in size for the fluid channels, I can put a 4-function calculator in 1 cubic foot.
Box.
Huh?
Put it in a box.
Put it in a box. So a stack of clay plates, 1 cubic foot.
The other thing you can do is you can cast each one of those things using slip.
Yep.
And when you do, you get a thing that's about 3/4 of an inch by 1.5 inches by about 1/4 inch high. And you can put little holes in the bottoms of them and put little studs on the top of them.
And porcelain doesn't
And so
react
you
to
can
heat
make
the same way.
Lego electronic circuits.
And let's
That was
say,
the L word he didn't want me to mention.
and let's say that all of this is really pie in the sky and it's only 4% as efficient, so 27. So now it's a cubic yard. It still changes everything.
Yep.
Still changes everything. And so,
And this is something
we
that-
absolutely positively know that the material to do it is in Grantville, because we've looked in the Mannington Public Library. We know the material is there. We know that the logic diagrams for 4004 and 8008 circuits, our processors are in the Mannington Public Library. We know they're there, 100% certain. So, can this be done? Yes. So, that's cool so far, right? And so, we call that the aqualator. Okay?
Hey, Rick?
Yeah.
Look, as you know, I'm an ignorant. What is 4-function calculation? What is that?
Plus
Add
minus.
plus minus multiplied by. I'll even give you a
It's-
square root
yeah.
key.
It's
in a-
7th
in
grade
1
math.
cubic foot.
Okay,
How
all
many
right, but
places,
you could've just
How
said-
many places?
Yeah.
You could have just said basic math, but instead you had to make it more complicated.
High school teacher.
I know.
It
High
never,
school,
I last taught physics in
got a
high school in
D in
1983. It never wears off. Go ahead.
All right, never mind, keep going. Next
Okay.
one is 404.
Okay, a 404 was the first general purpose microprocessor, and 8008 is the first one that ran the CP/M operating system. This is a real computer, okay?
Which one, the
The
888?
8008.
8088.
No. You can run CP/M on an 8008. An 8080 is an upstep from that, trust me.
But the
but
first,
software is in Mannington too.
The software is in
probably.
Mannington too.
absolutely.
Although this would be different software because we're not going to copy the circuit exactly. But give me a minute.
yes,
But our 1 cubic yard CPU includes about 6 or 8 K of RAM. Okay? Now, that's a lot of RAM. I know, your laptop has gigabytes of RAM now. I don't care. 4 or 8K is a lot of RAM, okay?
How
My
much does a
Apple
lunar
II
lander use?
My Apple
The
II
lunar
that I
lander
bought in
used 16K.
1977.
And the
4K
space
RAM.
shuttle used
My
16,
first one was
32K, I'm sorry.
16K.
Yeah, my
My
first
first and
computer that I programmed, an IBM 1130 programmed with cards with a line printer that had a wheel at every position along 132 spaces, and they went and went clunk. That had 1K of transistor memory. Every bit was an individual transistor.
oh my god.
The Apollo spacecraft had 5K of RAM.
Exactly. So don't discount this. This is a very real machine.
The
Yeah.
reason I asked about places is the 1 cubic feet compares fairly well to this ancient mechanical
The Antikythera
calculator
machine.
that I used
Right.
at MIT at one
Right.
point.
Sure.
They had it in one of the labs and
Right.
I just had to use it.
Right.
It was probably half a cubic foot. Obviously, it went out to a lot more places than a slide rule
Right.
did, but not a huge number.
This would be your typical calculator level of precision, 10 or 12 decimal places. Now, displays. Well, displays. For a calculator, displays are simple because I only have to give you numbers, right? And so I literally could give you, just pop outs in each place that, well, I could do 8 segment pieces, but I could just give you 0 through 9 with a pop out where you'd read the ones that were sticking out. I mean, I don't care. 4-function calculators are easy, right? And when we get into CPUs, what are you going to use for a display? Well, there are a lot of ways we can do displays. They're going to be low resolution. They're going to be character oriented because that's the way computing was until the 1980s. And trust me, we ran a lot of computer programs before that.
We did.
But, so they're going to be low resolution, character oriented displays, right? But that's not weird enough, really. I mean, I've got water powered computers made out of clay, molded and stacked with wax. And their keyboards, of course, are organ keyboards, right?
Right, because we have
Because I've got
organs.
valves attached to each key, so the keyboards are organ keyboards.
And there's plenty of downtimers.
There's plenty of organs. So